cloud server. Oh yeah, it did go fine. Great. We said we will have a class today and one on Wednesday and one on next Monday, and that is going to be like the 14 lectures, and we're pretty much done, right? And on Wednesday, I thought we could do it on the same time. However, I have a German exam, which I'm totally going to fail, and I'm saying it on record. But I mean, it's going to be at the same time. So can we have this partition theory course at 1 p.m. on Wednesday? 1 p.m. sounds good? Okay, I'll find the classroom, which is going to be most likely the Science Park 2 meeting room that we met before. Yeah.
Sorry, can you hear me?
I need to turn up the volume, but I think I can hear you, Barbara. Can you speak again? Yes.
I don't know if on Wednesday there's some combinatorics seminar or not this week from RISC.
Let's check. That's a good question. Let's see if there's a combinatorics seminar this week. I believe that they have something going on. I just saw an email from them saying that they will keep on doing the combinatorics seminar in the hybrid mode. So this week it will be Nicholas Sumut and Sylvie Radu. So it says, and it is from 2 to 4, right?
Right. Okay. So who is? Okay. Yeah. 2 to 4. Okay. Then, but one will this overlap? Maybe overlap a bit with that one.
Should we try to do it 12:30 to 2 p.m.? Would that work for you better?
Let me just check. But that is a hybrid. Okay. But we have
both are hybrids. Yes, I know the RISC talk is hybrid. I know ours is hybrid as well. So.
And do you know if there is a recom seminar this week also? I have no. I didn't remember.
I mean, if there's also a recom thing, then it's yet another mess. But I mean, we can handle that. So okay. I didn't want it 12:30 because I know that it's lunchtime. I mean, I would expect people to go to lunch.
Yeah, it should then 45 is fine for me. It's fine.
So 1 to 2:30 is fine for you, or no?
I mean, this you said 1:45. Is it not so good, right? Or
no, I said 1 p.m. to 2:30 p.m.
2:30, and the RISC seminar starts at 2, right?
Yes.
And 12:30 is not good.
So there's some overlap. I'm sorry about that. But what I can do, the best I can do is like that I'm recording the courses, right? I'm recording the lecture, so you can just watch it.
Okay. Yeah.
Sounds good? Yeah, then let's do it that way. So have the recording and we can always have the chat. I mean, I'm always available to have a Zoom chat or to talk in person. Okay?
Yes.
Then let's go for 1 p.m. To 2:30 p.m.
Okay.
24. Next week, Friday, we canceled that one.
Yes, we canceled that one already. So it's 13, 15, and 20, and we're done.
Okay.
So today 13, then 15th at 1 p.m. and 20 at the right time, and we're pretty much done with the course. Yeah. Okay. So we have done a lot of partition identities in this semester. So I have done a lot of like this set has the same amount of elements of that set. There are multiple reasons for that. I mean, one thing, it is really interesting to see that like two completely different sets have the same number of elements, the same number of combinatorial objects coming from different families. And another reason is this is where like you really touch number theory with combinatorics. Like this is where you see that like sums becoming products, like these analytic identities happening in the unit circle. If you want to keep them analytic.
It seems identities for always for partition, completely different sets of partitions.
Exactly. Yeah.
But are there other combinatoric things, other combinatoric quantities that we have identities to the number of partitions?
So number of partitions to other combinatoric things. There are like number of partitions that are related to Fishburne numbers and things like that. So there are some related objects that you can translate, but I mean, yeah, in the theory of partitions, you usually want to have identities in between partitions. That's why we focused on them. But yeah, there are some other objects as well. At the very least, there's like this Fishburne numbers. There are these compositions. Compositions are just partitions again, but you don't have the order of decreasing. So you can just have like all these increasing, decreasing sets and all that. But what I wanted to focus now on the last like couple of lectures is, in the last lecture, I focused on, we did some bounded identity. So we looked at the Q binomial coefficients, where we can bound the number of parts and the largest parts. This time I want to do congruence properties of partitions. So some other arithmetic properties where you see that additive number theory kind of matches, like, or at least touches multiplicative number theory. And there's also like huge group of research going on in that. A couple of people that do that type of research would be Nicholas Smoot and Sylvie Radu, who are going to give the talk that Barbara was mentioning. So I want to cover some number of some number of like early results in congruence relations. And after that, I want to talk about asymptotics, like how fast are these numbers growing? How fast are these PNs are growing? And that should give us a good coverage of the questions in the theory of partitions. So we have a lot of partition identities. Me saying that we don't have enough, we can have always more partition identities whenever we can find them, but it's a really rich system that we don't understand completely, and it goes towards like the representation theory through this energy matrices and like things like that, through these dimension formula of coming from the Kakbal. There's also this holonomic function there, things are recurrent, so we use this machinery to prove these identities. Then another question would be, are there any arithmetic properties? Although we don't have a formula for these Pn, and there are, I will just talk about it in a second, which is going from the additive number theory to multiplicative number theory in a sense. And then there's the asymptotics, which like how fast are these guys growing? How fast are these things growing? And which also goes towards like the research of Gargi, for example. Like these are growing, are they growing like similar enough to integers that we can have other properties? For example, the log concavity, which turns out, yeah, we have. So here's the chart that I want to start with. So I have listed the number of partitions for some value. So I started with P0, then the number of partitions of P1, then number of partitions of 2, 3, 4, then partitions of 5. There are 7 partitions of 5. It's just 0 mod 5. I just put them in columns. And I'm not the first one to make this list. And I'm pretty sure I'm not going to be the last one. But one of the first people to make such a list was McMahon, of McMahon analysis. If you are familiar with like the rational functions and looking for the positive solutions or Diophantine system solutions. And he calculated the first 200 numbers for partitions. And Ramanujan saw it, and he directly observed that whenever you have 4 modulo 5 parts, they seem to be divisible by 5. You see, it's 5, 0, 5, 0, 5, 5. So he observed, Ramanujan observed that P5M plus 4 type partition seems to be 0 modulo 5. Which there is no reason why it should be, because I mean, it's just the number of partitions, and we don't even have a clear formula for these P numbers. We have a clear formula for their generating function, but turns out, yeah, this divisibility property actually is there, and we can prove it, which we will do. He also observed these things. So if you were to look at these numbers, just jumping and that and that. So if you were to look at Pn 7n plus 6, 7m plus 6, let's say, these seem to be 0 modulo 7. I'm hoping to prove this one as well. And he then observed, which is going to be hard to see here, it is P11m plus 7, 11m plus, no, this is 5, this is 6. Yeah, so it should go 4, 5, 6. So 7m plus 5 and 11m plus 6 is congruent to 0 modulo 11, which is harder to prove. So yeah, apparently these partition numbers, the number of partitions satisfy some congruence properties. And it is not so clear why it should be the case, but they do, and we will see some proofs of that. We will see Ramanjan's proof of the first two, and maybe then Kohlberg's proof of a dissection of this generating function. But it's a really interesting result in 1919 that these additive objects, the partition counting object, somehow has some arithmetic properties inside of it. So it has some multiplicative properties as well. And for us to prove this Pn P5m plus 4 is congruent to 0, and the other one as well, modulo 5, I need to revisit the Jacobi triple product identity once again, just so we remember what it was and get some necessary results as well. So we define the JTP, Jacobi triple product identity. We prove this as well as a bilateral sum from negative infinity to infinity. Let's say n, z, and q to the n to the power 2 is the symmetric product. So it is minus zq, comma, q over z, and it's minus q over z, comma, q squared and q squared sub infinity. So it was three products turning into a bilateral sum, and it was symmetric in z. So z goes to 1 over z is fine. We had one particular result of that, which was Euler pentagonal number theorem. In this, we just take q to q over 3/2 first, followed up with z goes to q to 1/2. We did in lecture 2, so we can check the left-hand side just in a second. So it is n goes to negative infinity to infinity. If we were to do that on the right-hand side, I think I need a negative, so it's negative q/2. So q goes to q 3/2, then I add a 1/2 to that, so it goes to q to the power 2. The second one is q goes to 3/2, then I have q 1/2 on the bottom, so it goes to q. And this is q goes to 3/2, so it is q cubed, base q cubed sub infinity. This is 1 modulo 2 modulo 3 modulo 3, so it is all the modulus classes mod 3. So it's just q infinity. And on the left-hand side, we have that negative is going to be negative 1 to the n, and we have q 3n to the power 2 minus n over 2. So 3n over 2 coming from here, minus n over 2, or plus n over 2, however you like it. Totally fine. It's bilateral and it's symmetric in n. So this is another one. Now I want to have not q infinity, but I want to have q infinity cube. I want to use JTP again, maybe not so directly, but I aim to get q sub infinity cube. Yeah, for that I need to change this q squared back to q. I know that, so q squared must go to q. But it's not so easy to choose what z is supposed to be. You see? Because if I were to take like z to q 1/2, then yeah, one of them becomes q, but the other one becomes 1. So I would introduce some sort of a 0. So let's take care of that portion first. But this is my goal, that I want to see at the very end q sub infinity cube. So for that, I will write the JTP again. JTP z n q n to the power 2 is that minus z cubed minus q over z and q to the power 2 q squared sub infinity, and from minus infinity to infinity. And my goal at the end goal is to get q sub infinity cube. And I already know that there's going to be some issue because when I take q goes to q squared goes to q, this becomes minus z q 1/2. This becomes minus q 1/2 z. This becomes q sub infinity. So I get one of them. But for me to make the other two, I need to just make some adjustments, because if I plug in q to be 1/2 or q to be negative 1/2, this guy becomes a q, fine, but this becomes 1, and I introduce a 0. Or the other variant, if I take this one to be negative 1/2, if I take this z to be that, then this guy becomes a q, then that product becomes a q, but this one becomes a 1. So I introduced that like 0, so there should be some adjustment that we need to do. Perfect. And let's do that. So I took that guy, which is fine. Then I need to adjust things, but maybe this is not the way to start. So let's take care of that problem first. So first, let's take z to, let's make this thing, let's take z to negative z over q. Why not? This will make our original Jacobi triple product identity to be -1 to the n, z to the n, q to the n squared minus n. And from minus infinity to infinity. And over here, I will have a z, because I mean that minus z canceled, and this guy is going to be a q squared divided by z. Right? That q made it into q squared, negatives are gone, z is still on the bottom, and this guy is q squared sub infinity. Okay, we're one step closer. So now, if I forget about this portion, if I plug in z to be 1 and then shrink q squared to q, I would get 2 q infinities, right? I mean, I have 1 and 2 q infinities. And maybe I can just take care of that z as well. I know that it will create a 0, but maybe we can just cancel it. And the way that I want to cancel this, I will just divide both sides with 1 minus z. Right? If I divide that side with 1 minus z, this would just cancel that first term, this first 1 minus z term, that is going to be canceled. And the next guy is going to be z q to the power 2. Right? Because the step size is q squared. Okay. So we now get this formula. And as you can see, now this is okay. If I plug in z to be 1 on the right, it becomes q squared, base q squared. Then I can just shrink down q squared to q. I would reach my goal. Okay, we paid the price on the right. And now we have a problem on the left. We now cannot plug in z equals 1. Right? So how is that going to work? If you believe me, L'Hopital's. If you don't believe me, we need to play with things on the inside. But please believe me, this is z going to 1. We cannot take care of it. But after all, as z goes to 1, we already know that this has a 0 because we already know what it's supposed to be. It is the term with the z of that. So this has a 0, that has a 0 on the top and on the bottom. So as z goes to 1, we will need to take L'Hopital's rule. So as limit z goes to 1 from the inside of the unit circle, just to keep everything convergent, we need L'Hopital's rule. L'Hopital's rule. And that is for the left-hand side. The right-hand side, we can already plug in z equals 1. We know what we're going to get. So once we do that, on the left, we will have something that we have not seen before, but it's going to be okay. That z to the n will drop an n down. There's going to be z n minus 1, right? And q n squared minus n divided by -1. Again, it's a bilateral sum. It is still bilateral. The thing that we haven't seen before is we haven't seen any coefficient other than plus minus 1 before inside the sums. And this is still limit z goes to 1. And on the other side, we know we can plug in z equals 1. So this is actually q squared sub infinity q, which is what we want for our goal anyway. We will just shrink down the q's to q squares again. Now, on the left-hand side, I can also plug in z equals 1. The problem of the z on the bottom went away, right? So let's tidy it up and let's write the formula. Once I plug in z equals 1, we will end up getting this -1 to the n minus 1, sorry, or n plus 1, however you like it, and I plug in z equals 1, q to the n squared minus n, and from negative infinity to infinity is equal to q squared sub infinity cube. Great. So now let's modify things to the way that we want them to be. So we will shrink q squared goes to q. That cancels that q squared, that cancels that q squared. Right? I changed the q to q squared, q 1/2, and then they're gone. Cool. Now we have these two formulas, and this and this other one. -1 to the n, q to the 3n squared plus n, or minus n over 2, and negative infinity is equal to the q infinity. So this is Euler Pentagonal number theorem, an outcome of the JTP. This is another outcome of the JTP, and this is actually a really nice outcome. Okay, we can even modify this to look better, to look more fitting for our purposes. And the reason why I want to do these things is like I will use these pieces in the proof of these congruence relations. I just want to do the background work so that we can just use them when we need it. Now, here, I will, I want to write this in a better way. So this is bilateral. I don't want to write it as a bilateral sum, but I want to write it as a single fold sum. Is that okay? So let's write down some values of this and see if we can combine this term into something simpler. So let's say these are the n terms. Now let's see what we're going to get. So when n is equal to 0, we have, so the summand itself, so when n is equal to 0, this is n, that is -1 to the n minus 1, and this is, so n squared minus n over 2. So I'm just combining the terms, then we can just look at the summand at the very end. So when n is equal to 0, we have a -1, and this guy is a 0, right? So after all, we also have the n being 0, so this is 0. It goes away. What about n equals 1? Then I have a positive 1. This guy is also a 0. I thought 0, wrote 1, which is fine. So 1 squared minus 1 over 2 is just a 0. So the summand itself is 1 times 1 times q to the power 0, which is just 1. Okay. 2, this is a -1, right? -1 to the n minus 1 is a -1. 4 minus 2 over 2, this is actually a 1. So this is, the summand is negative 2 times, that's n is coming from here, -2 times q to the power 1. 3, good, it's gonna be fine. So this is +1. 9 minus 3 is 6, divided by 2 is 3. So this is going to be +3q to the power 3. Fine, let's write another one. 4 -1, then it is 16, 12, 6. So it is -4q to the power 6. Fine. Let's now look at the negative side. So this is -1, so there's a +1. So here's where I want to break things anyway, or like here. So the 0 doesn't matter. So -1, -1 squared, -1, so it is just 0. It should be 1, yes. You're right. It should definitely be 1. So this is 1, great. Then I have a 1, then 1, so it is negative q to the power 1, if I'm right. So because we get an extra negative due to n, so this n pops out another negative. So keep that in mind. On the left hand side, on the negative side, we're getting an extra negative. So -2. So this is a -1, but I will get an extra negative because of -2 at the end. So -2, it is 4 minus 2, so it is 6 divided by 2 is 3. So it is minus plus 2q cubed. Okay. And so there was a negative, another negative came from here. That's just a necessary information that we need. So 1, so this is 3. I suggest that this will be 6. Let's check it. So it is 9, then minus 3 is plus 3, so 12 divided by 2, 6, and this is going to be a negative 3q to the 6. Well, a great thing. And this is a great thing about triangular numbers. So when you just take the negation and with one shift, they're the same things. You see the exponents are the same. So I have q to the 1, q to the 1. I have q cubed, q cubed. I have q6, q6, right? So maybe I can combine them. It seems that this sum is 1 plus, or not even with that. Let's write. So it is 1, then minus how many q to the 1s? Negative 3q to the 1s. Then plus, well, 3 plus 2, 5q cubes. Then minus 7q 6s, plus I would suggest that this is 9q 10s, and it will go this way. So we have triangular numbers in the exponents, and look at the coefficients. The coefficients are all the odd numbers. So they just combine to be the odd numbers, right? Yeah, because it is just like n, then n minus 1. So you add them up. I mean, it's extra negative, but it becomes 2n minus 1. So if we were to write them up, this is a sum n from 0 to infinity, negative 1 to the n, then 2n plus 1, q to the power, n squared minus n squared plus n over 2. Just to match it up. At 1, it is just q to the 1. At 3, it is cool. Now we have a even better looking formula. So we will need this Euler pentagon number theorem and this formula, which is negative 1 to the n, the odd numbers 2n plus 1, q to the n squared plus n over 2. And this is the q sub infinity to the q, from 0 to infinity. Perfect. So we will make use of these two to prove that congruence relation. Let's do that. Now, we know, now really the proof of this P of 5m plus 4 is congruent to 0 modulo 5. So that's like divisibility thing, the first Ramanujan congruence. Now, we know that the generating function for these Pn of xn, 0 to infinity, is given by this product. I'm really writing it out, 1 minus x to the I from 1 to infinity. This was the original generating function, right? So I can switch it up a little bit and write it in this format, just so we have that 5m plus 4 case in the 0 modulo 5 residue classes. So I will include an x here, which will include an x here. I'm just multiplying with an x. Why I'm doing that? It's just how the proof goes. It's just a normalization factor. And the reason is you want these 5m plus 4 terms to appear with x to the 5k type terms. So you can just identify them easier. That's the reason on the background. So on the back of our heads, we have that. Okay, so I will write this even in a slightly different way. So now shift that n back. So it is x to the n. This is p of n minus 1. Up, and greater or equal than 1 to infinity. Now you see now that 5m plus 4 type terms are going to come with the 5m. it is just x divided by the product of 1 minus xi and I1 to infinity. Cool. Now, I would like to remind you of another theorem that we will use, and that is Fermat's little theorem. After all, we're doing number theory now, right? So here's a great number theory result. For p being a prime, and 5 is, so we will use it just in a second, for p prime. And x can be 0 as well. We will use non-zero x, but it's fine. For p being prime, x to the power p is congruent to x modulo p, right? Or x to the p minus 1 is 1 modulo p. Either way, you can write it. And if you were to write it this way, then x needs to be non-zero. And x is non-zero modulo p. So it says, yeah, I mean, yeah, if you were to just raise it to the p minus first power, then it will become 1. It also says that x to the p is congruent to x modulo p. It even says that for any non-zero x, there's an inverse in the finite field. Well, how are we going to use that? I want to multiply this guy with this term. I want to multiply that guy with this 1 minus x to the 5m term. The product of m from 1 to infinity. Because I know that these 5m plus 4, like the coefficients that I'm looking after, are coming with x to the 5k type things. And I don't want to change their residue classes. I don't want to shift them to other residue classes so that it will be harder for me to track them. But I want to shift them so in some way with 5m's that the residue classes are still in front of the x to the 5k terms. But this normalization factor is going to give us some more play. I want to multiply with that for some good reason, and to be able to also use these two formulas that we just looked at. And now the key with Fermat's little theorem is that this guy needs to be congruent to the product stays the same, m stays the same, 1 minus x to the m stays the same, but this to the power 5 modulo 5. Would you believe that? If not, we can do this through the binomial theorem. Yeah, 1 minus x to the 5m. This is the binomial sum, 5m minus k, x to the 5m minus k from 0 to infinity, right? These are all divisible by 5, except when you touch one of the boundaries. And that's how you would pull that. So it is coming from the Fermat's little theorem. Great. Now you see that like this extra 5 will introduce all these terms that we have done before. So let's multiply them. Let's combine them and see what we have. So from here we have this guy, from there we have this whole thing, and I will multiply them together. So I will get this sum pn minus 1 x to the n, and from 1 to infinity times this 1 minus x to the 5m. So m from 1 to infinity, this the left hand side is multiplied, is congruent to x times this 1 minus xi will cancel one of them. So it is x times this pi infinity m from 1 minus x to the m to the power 4. So I have one of them in the denominator. I have 5 of them in the numerator, modulo 5. They're not equal. They're just equivalent. And modulo 5 in prime powers, we're fine. Good. This is 4. I don't know what to do with 4, but I know formulas for that to the power 1 and that to the power 3. So that thing to the power 1 is Euler's pentagonal number term. That thing to the power 3 is this new formula that we found. So maybe we can just write them as 1 times 4 and look at that. This is x, this product 1 minus x to the power m, from 1 to infinity, and the product of that 1 minus x to the power m to the power 3. I'm being quite liberal of where I put the power, but it's the same. I can put this 3 inside, outside it's totally the same. This I will write with Euler pentagonal number theorem now as a sum. And this I will write it with the other new formula that we found as a sum. Then we will check the coefficients, because after all, here I'm looking for the P5m plus 4s. This P5m plus 4s comes with the coefficient x to the 5m from this guy. Now I'm including some other x to the 5k's, but the residue class in the exponent of x is 0 modulo 5. So I will hunt down these 0 modulo 5 coefficients later on. Right. So at least it makes some sense, right? All right, let's write this again. So this is Pn minus 1 x to the n, and from 1 to infinity times this product infinity m from 1 to infinity 1 minus x to the 5m. And it is congruent to this time x times, I'm just writing the sums, the sum -1 to j. Let's write it that way. So q 3j minus j over 2. And j is from negative to infinity times the sum k from 0 to infinity -1 to the k, 2k plus 1, and x to the power k squared plus k over 2. Perfect. And this is modulo 5. Euler pentagonal number theorem in the first group, and the next formula that we found for the second group. And we know what we want to do. At after all, we want to hunt down the x to the 5m type terms from the left-hand side. So the best thing to check is, what is the exponent of x? Oh, this should be x. So I'm writing everything in x now. What is the exponent of x here? And how can it become 0 modulo 5? So the exponent of x on the right is 1. So coming from here, plus this 3j squared minus j over 2, then plus this k squared plus k over 2 from here, right? And I want to understand like what residue class this is, and I actually want to find where this guy becomes 0 modulo 5. So let's try to solve this. So we're really down to the elementary number theory portion of this. 2 has an inverse in modulo 5. I can multiply everything with 2. So it's 2 plus 3j to the power 2 minus j plus k squared plus k, convert to 0, mod 5. Cool. Let's play with these things. So this 3j, I can write it as minus 2j squared. It's fine. This minus j, I can write this plus 4j. I'm just trying to combine things and write some square roots. This plus k squared, I can write this minus 4k to the power 2 and minus 4k plus a 2 modulo 0 mod 5, congruent to 0 modulo 5. So a lot of just even numbers. And this guy looks like almost a perfect square if you combine that -2 out, but I need a +1, right? So this is -1 and the +1 after the -2, so it is actually a -1. So j minus 1 to the power 2. Same type of idea here. This is yes, this is so it is 2k plus 1 is where this thing should come into play too. So 2k plus 1 squared. And for that, I need a +1 for the first one. And for the second one, I need a +2. And I also have a +2 coming from here. Let's do it. I'm like following my notes anyway, but so j squared minus 2j plus 1, right? So this would become -2. That would cancel that. One of them. So there's -2 plus 4, which fits that guy. If you were to do this one, it will be -4k squared. Then 2 times first time the second. So it is 4k minus 4k. And -1, and -1 plus 1, they would cancel out. And that +2 comes from the same. Okay. So, all right, we didn't do any arithmetic errors for now. And it's a surprise. But yeah, we wrote it as a sum of 2 squares, basically. So 1 plus 2 plus 2 just will go away, modulo 5. That's just 0. So we ended up as with like this guy. So see, this is negative, that is negative. I can multiply everything with positive or just carry them to the other side. So 2j minus 1 to the power 2 plus 2k plus 1 to the power 2 is congruent to 0 modulo 5. This is what we end up with. Now, how can this happen? We can just check the values of j and k, right? So for this, let's check j minus 1 and the powers of the j minus 1 to the power 2. So if it is 0, that is 0 modulo 5. So these are multiplied. If this is 1, then the square is 1. If this is 2, then the square is 4. But I also have like this 2. If you want to add it, like just this is 2. So it was 4 times 2. This is just 3, right? If it is 3, then 9, which is so 9, 18, it's another 3. Yeah, it's -2 anyway, right? Exactly. So it is -1. It's going to be 2. So it's 4. Okay, so this guy can only be 0, 2, or 3 mod 5. We learned that. And after we're looking for like this 5m terms, right? Let's do the same thing for the 2k plus 1. So here is the 2k plus 1 and 2k plus 1 to the power 2. This is also modulo 5. And this is even going to be easier because I mean, no matter what k is, this needs to be basically odd. I don't think. Let's go crazy. So 2k plus 1. If k is 0, then this is 1. Then the square of that is 1. Modulo 5. If k is 1, then this is like 3 modulo 5. Then the square of that is 4 modulo 5. If k is 2, this is 0 modulo 5. And the square of that is 0 modulo 5. If k is 3, then we're back. So 6, 7. I would end up with like 3 again. Am I correct? No. Yeah. Yeah, it's going to be the same thing. That's the point is like they're only so this is this is 4, then it's going to be 1. Yeah, there are only 3 residue classes, which is saying that this guy can only be 0, 1, or 4 modulo 5. Cool. Then let's look at combinations. I'm going to combine 2 of them and make 0 modulo 5. What are the possible combinations? It can be 0 and 0. So this 2j minus 1 squared and 2k plus 1 squared might be 0 and 0, then it would be in addition 0 modulo 5. Are there any other combinations? So 2 and 1, no. 2 and 4, no. 3 and 1, 3 or 3 and 4, no. So this is the only combination where I can actually get that 5m type things. The only combination that gives me 0 modulo 5 on the right is that this 2j minus 1 squared must be congruent to 0 mod 5, and this 2k plus 1 squared gives me 0 modulo 5. Well, the great thing is, if 2k plus 1 squared is 0 modulo 5, if I'm here, what is the congruence class of 2k plus 1? 2k plus 1 is also 0 modulo 5 in these certain situations, right? If 2k plus 1 is 0 modulo 5 for these type of exponents, the right-hand side is 0 modulo 5 for these type of exponents. So whenever you see x to the power 5m, you have your coefficient is divisible by 5. Is the back tracing making sense? So we figured out the only way the exponent can be 0 modulo 5, the exponent of x can be 0 modulo 5 is this 2j minus 1 squared plus the 2k plus 1 squared must be 0 modulo 5. That in turn said that 2k plus 1 squared needed to be 0 modulo 5, so 2k plus 1 needed to be 0 modulo 5, but that also appears in the coefficient. So if 2k plus 1 is 0 modulo 5 in the coefficient, anything on the right and on the left that comes at x to the power 5m, like a multiple of 5, yeah, right? Yeah, exactly. So, but the coefficients must be on this side, the coefficient must be divisible by 5. Now, it is either this coefficient or the coefficient coming from this, of course, right? So the coefficients coming from this side for 5 modulo 5m, like everything is divisible by 5 here. So the coefficients that are going to come from this side is p of 5m plus 4 type. Nothing else, because these are the ones that comes with 5x. These are already just, I mean, divisible by 5. So it's either these p of 5m plus 4s that are divisible by 5, which is the thing that we want to prove anyway, or it is these guys from the other side that are making it divisible by 5. Which one do you think is the case? One more time. Let's write this again and let's finish the proof of that portion. So we already said everything that we needed to say. So Pn minus 1, x to the n. So it is n goes from 1 to infinity. This is an induction proof after this, but we don't even need that induction portion that much. We can argue it well enough that there's no doubt that this is the case. And this was x times the EPNT. Times this portion, which had a 2k plus 1 inside of it. So it was another sum with 2k plus 1 inside of it. And this guy became 0 modulo 5. When we look at the exponents x to the 5m type. The exponents for x, they're divisible by 5. And over here, when we look at the exponents of 5m type, we were getting some from here. I mean, all of them are that way. Or we're collecting these 5m plus 4s, which also come with this 5m, something from here. Right? So at first, the smallest one, this needs to be divisible by 5. Then the next one is just going to be like a combination of those. It will show the next element in this sequence is going to be divisible by. So the first step is that P of 4 is 5, which is divisible by 5. Then in the next step, when you look at the x to the power 10, it will show that P of 9 is congruent to 0 mod 5. And it will go this way, right? You can also take it as this is an Euler's pentagon number theorem. Again, EPNT. The coefficients of this guy is always plus or minus 1 whenever it gives you a coefficient. So these are never divisible by 1 because of the Euler's pentagon number theorem. But we know overall the whole thing is divisible by 5 on these coefficients. So it must make that P of 5, it must show that P of 5m plus 4 is divisible by 5 for every m. Really interesting result, right? And it's classical. It's a really classical result that you need to do some manipulation. You need to do some case analysis for the J and K to make sure that the exponents are 0 modulo 5. And yeah, it works. Do you have any question about that? The interesting thing, and like the thing that we need to keep in mind,
How much of this proof could you somehow get? How to choose the things as we choose them, or how much that's just trying out a lot of things and trying to work.
that's true. Yeah, I mean, it's
If you just want to make it fit everything, could you go from the back and see how you need to compute things, or just try out the fact?
I don't know how Ramanujan proved it. So this is Ramanujan's proof. And I mean, he definitely had a different mindset and different way of thinking. I would expect that he already knew a lot about the Euler pentagonal number theorem, and he already knew that like a coefficient of this 2k plus 1 type term would help. But it's, yeah, I mean, this setup, I mean, it's not so natural that you need like this setup. There are better setups as well, but you need like more involved machinery. Like you need modular forms and things like that. And there are actually there's active research going on in these type of identities of congruence relations. And in that, like they're using modular forms all the time, or modular functions all the time. And one of the, I mean, I can even like just name drop here, just because we're in LIMS, that one of the big names in this research, which is also said to have an algorithm, is the Radu's algorithm. That when you have a guest congruence relation for a partition or partition related function, you have a guest relation, you want to know if it is true or not. The steps that you should take are called the Radu algorithm, and it's named after Silvio Radu in RISC. And that's a different approach. That is a complex analysis approach that he is using, that because these are meromorphic functions after all, when you look at their series, they must have the same number of poles and same number of like zeros and everything. So you fit a function to your series with your claim. You try to write your function in a different way where it shows this divisibility property clearly, which is one of the proofs that I want to do here anyway. Maybe not today, but the next time. And then you show that, yeah, these two complex functions fit in every cusp, every issue. And if they fit one-to-one, if they have the same number of poles with the same residues at every pole, then you know that they are the same function. And then you can get the divisibility property using that. So to put it in concrete terms, for example, you would like to show, to prove the same theorem, you would like to show this. So P of 5m plus 4 of x to the m. So this time I'm not like, I don't have the whole thing. I have a sift of the thing. So I'm just only jumping over these P of 5m plus 4 terms from 0 to infinity. If you can show, for example, that this is 5 times this generating function, I think this is what it is. So it's m1 to infinity and 1 to infinity. If you can show this relation is true, and this is a true equality, not a congruence, then everything is divisible by 5. The way of doing that is you need to be able to sift that, the whole sum that you have, and using the properties of the modular function. This is like the portion where the modular function comes into play. So you need to, from this Pn minus 1 xn, you need to modify that so that you erase a lot of terms. P of 5m plus 4 x to the n is what you want to get. And later, this is a complex value function. This is a complex function, this is a meromorphic function. And so is this. You check that, yeah, they have the same poles, and at every pole, their Fourier expansion, they're not Fourier, their Laurent expansion are the same. The poles are the same, at least, right? Which shows that when you take their differences constant, you show that constant is 0, then you get your what is called a witness identity. That it gives you a witness that this thing is divisible by 5, like right away. Or for 7, for example, for the 7m plus 6 version of this, there's a 7 portion of this plus a 49 portion of this. So you show this, it's a witness identity because it shows you that things are being divisible by 7, like right away. But it's a different machinery. It's a somehow harder machinery. The version that Ramanujan gave is more hands-on, and somehow the setup is different, but that's what it is. All right, let's do modulo 7 maybe. So let's jump this. We will talk about this in the next time. Not necessarily using Silvius method, not necessarily using Radu's algorithm, but I want to prove it using Kohlberg's method, which is solving a linear system. But for more involved things like Silvius, the version is like much more applicable, of course. So let's prove that P of 7n plus, so it was 4, then this is 5, is congruent to 0 mod 7. This time I will do it exactly as the Ramanujan did it for the 5 case. And again, the idea is like this is 5. So I want to shift my function like twice and from 2 to infinity so that these type of coefficients appear as the coefficient of the exponents of term type x to the 7n. So I shifted twice first, which in the generating function would mean that I'm multiplying with x squared, right? Okay, the same deal. I have x to the power 7n here. I want to keep that trend. So I will multiply this thing with 1 minus x to the 7n, and from 1 to infinity. So this is also giving me x to the 7n type terms. So everything is, the terms that I'm looking after are the coefficient of exponents that are divisible by 7. Okay. On this side, the shift by 2, we already included that. We have the generating function for the number of partitions, I from 1 to infinity. And this guy, I will just multiply it in for as is for now. So this is x to the 7n, and from 1 to infinity. Now, again, the same trick. We move from the equality to the congruence modulo 7. This pulls that 7 out. Really the same trick. Pulls that 7 out, and even better, cancels one of them with that. Now what do we have? We end up getting, this guy is congruent to x to the power 2, then 2 of these cubic versions. So this is 1 minus x to the m. And this is 1 minus x to the k to the power 3 to the power 3. And we know the formula for this, and this is modulo 7. So you see, now we can write these down. So this is x to the power 2, and some -1 to the m, q to the m squared plus m over 2. And I forgot this 2m plus 1, right? That was the main deal that I needed, but 2m plus 1 is needed. And here, that's -1 to the k. I'm just using the same type of thing. 2k plus 1, q to the power k squared plus k over 2. These are bilateral again. And this m and that m are not the same. And that k and that k are not the same, but I'm just trying to keep them the same so that we know that they're coming from the same terms. So now what are we going to do? What are we going to solve? We know the terms that we're after, the things that we observed, come with the exponents x to the 7m, whatever that exponent might be, but I mean something divisible by 7. So I will collect the exponents of x here, not q, on this side, and make sure that it's 0 modulo 7. And we can solve that. It is not so bad. So I have 2 plus m squared plus m over 2 plus k squared plus k over 2 is congruent to 0 modulo 7 is what we want to solve. 2 has an inverse in modulo 7 multiplied with that. So 4 plus m squared plus m plus k squared plus k congruent to 0 modulo 7. I need to play with it again. So this is, I don't need to play with it. Not so much. But that's really good. Okay, so yeah. Why not? Oh, I need to play with it. Okay, okay. Yes, that's, I wouldn't have guessed it. Exactly, but I mean, even before that, we need perfect squares. And for perfect squares, apparently the way to go is you multiply it with 4. So it is 16 plus 4m squared plus 4m plus 4k squared plus 4k is congruent to 0 modulo 7. And once we have this 4 and 4, this guy becomes 2m plus 1 squared. I will add the term that is needed, which is this -1 plus this 4k, 2k plus 1 to the power 2 minus 1, 0 modulo 7. Yes. So, why is it still a 16? 14, so it is 0, yeah, exactly. So that goes away, that goes away, that goes away. So 14, we have these two guys. So 2k plus 1 and that. So let's do that. If 2m plus 1 is something, modulo 7, what is the 2m plus 1? So if it is, so if this is 0, that is 0. If this is 1 modulo 7, this is 1 modulo 7, this is the square. If there's 2 modulo 7, that is 4. If that is 3 modulo 7, that is 2. If this is, yeah, exactly. So if it's 4, then it's 2, 4, 1. So it is like 4, 5, 6, right? Cool. And this is the same. So it's after all the same value anyway. So it's the same 2m plus 1, 3k plus 1. So 0, 1, 2, or 3. No, 0, 1, or 4 modulo 7. And this is also 0, 1, or 4 modulo 7. So these are modulo 7. I need the sum to be 0 modulo 7. Yes, it can be. Yeah, it doesn't matter at the end, but I mean, I shouldn't be forgetting that. Yes, these are the different residue classes in the square. These are the quadratic residues, modulo 7. So what combination would give me 0 modulo 7 after all? It's again just 0 and 0, right? So 2m plus 1 must be, I mean, this thing square must be 0 modulo 7. Same with 2k plus 1, but this tells me that 2m plus 1 must be 0 modulo 7. Now we will go back. We'll remember that in the formula, in the actual formula, we have that 2m plus 1 in the coefficient. So if we have that 2m plus 1 to be 0 modulo 7, then the coefficient is 0 modulo 7. And this one is also 0 modulo 7. Anyway, but yeah, so it would tell me that the coefficients of the terms with the exponent divisible by 7 on the right are 0 modulo 7. So they're divisible by 7, which means on the left, the exponents of the coefficients of the exponents of the form say x to the power 7m, whatever m might be, have a 0 mod 7 coefficient. And then we need
Oh, because in the first step, okay.
Yes. Exactly. Yeah. The reason is this guy. Basically. So P of 5, the starting point is like 7. But I mean, after that, yeah, it should be okay. Yeah, so if anything, there's like some issue with the initial condition, but I mean, no problem. It is divisible by 7. And yeah, so again, an induction shows that these terms of P of 7m plus 5 are 0 modulo 7. Once again, there's a different way of proving that using a witness identity. If you can show that the generating function for the sifted series is an identity that you can directly see the coefficients from, then I mean that's the proof. And that is usually what Radu's algorithm like aims for. That's what Radu's algorithm aims for. But I mean the roots of that before it became the algorithm is like coming from Kohlberg, coming from like some other people too. Yeah, and
can be written in some nice
no reason whatsoever. So that's almost an art form to be able to find a class where your functions create this witness identity. You can observe this divisibility property, but I mean, if you like, for example, here, like there are so many special choices, right? So in that one too, if you don't make the right special choices and they know how to do most of it, like using the modular function or the modular space, the weight of the modular space and everything, there's no reason like why your identity should witness the congruence property. Like you can, I shouldn't say always, but I mean, you might be able to find another complex function that fits your function, but not necessarily that it would show that the coefficient, that divisibility property is going to appear in the coefficients. So it's a really a different art form. And this is a different art form as well, but this is the classical. So one last word to say is that these are technical proofs. These are just like we play with these series and like get results type of proofs, but there are other proofs as well. So Freeman Dyson defines a combinatorial object called rank of a partition, and this rank is like quite simple to explain. Which I can do it next time. It can also, you can use the rank function, the rank generating function to prove these two congruence properties that we have proven here. But neither this technique that we talked about, nor the rank can prove this last one. The modulo 11 one. Modulo 11 is a little bit more involved, so this is 6. So you need a stronger technique, so that's why like these techniques grew. So Freeman Dyson said that, yeah, I mean, I found rank and it proved these things. Somebody will find something called a crank. He named it before he found it. And this crank will prove that one too. Later on, Frank Garvin, together with his advisor, George Andrews, defined this crank function. That is also not so hard to explain, and they proved this through combinatorial means, at least like through a combinatorial object as well. But there were already like modular function proofs of this. And like these are only 3 of them, but I mean, there are infinitely many of these identities. Like this congruence relations are really a different type of world, and this is a different type of research where a lot of energy is going in, because I mean, a lot of people that are interested in like modular functions, like the symmetries of functions, are also interested in like these type of number theoretic examples. Yeah, so let's leave it here now, and let's come together on Wednesday, where we do the same results, maybe in a Kohlberg way, so that we show that it's 5 of p of something divided by 5 of p of something else. So it proves the same result. And on the last class, or maybe next time, I will decide, I will talk to Gargi. We can talk about the asymptotics, because I want Gargi to present like her new paper as well. Okay, yeah, great. Thanks for coming. Thanks for being here. And I should stop sharing. I should stop the recording. Fine.
And